All right, disembodied head here. In the previous video, I talked about how an electron configuration represents a periodic table. And so in this example, we're going to go through that today. In this video, we're going to go through that. So we're going to start out with the first atom in the periodic table. We're going to start with hydrogen up here on the top left. Now, periodic table is organized from hydrogen to helium, lithium, beryllium, and so on and so forth. But there's some important things to note in the periodic table. Things like hydrogen and lithium and sodium that are all on that same row effectively behave in the same way. Why? Because they have a similar electron configuration. Conversely, fluorine, chlorine, bromine, iodine also have a similar electron configuration. And finally, things like helium, neon, argon, those are called noble gases, and they're a noble gas because they are typically unreactive. And the reason they're unreactive is because of the electron configuration and the behavior of those electrons. So let's go through this process and take a look at what's happening. There are a couple of rules that we're going to invoke. The first rule is the Aufbau principle. Aufbau. If I could spell, that'd be awesome. We need an F in there. The only F we want to see in organic chemistry. The Aufbau principle states we're going to fill the lowest electrons first. So we're going to fill the lowest electron orbitals first. The second rule we're going to invoke is the Pauli exclusion principle. And that tells us that electrons are either spin up or spin down in a specific electron orbital. No two electrons can be spin up, no two electrons can be spin down. They are going to mispair each other. One's going to spin up, one's going to spin down. And the third rule we're going to use is Hund's rule. And that says multiple orbitals of equal energy fill up each individual before going back and filling up with the different paired electrons. So multiple orbitals electrons fill up one at a time. Before pairing. So what do I mean by that? Well, like I said, this image here is a representation of the periodic table over here. And so let's start with hydrogen. Hydrogen has one proton. It'll also have one electron in it as well. And so if we're starting with hydrogen, the electron configuration for hydrogen just has a single electron spin up. Let's go through it like that. So that's hydrogen. If we then go to helium, atomic number 2, we're going to add another proton, and in order for that molecule to be neutral, again, that molecule, or that atom, needs to have a second electron. And that second electron is then going to fill down. So now this is the electron configuration of helium. And helium is inactive because both electrons occupy a filled orbital. So the next orbital we're going to go to, number 3, lithium. Lithium is going to have a single electron in the 2s orbital. And the next atom after that is beryllium. And beryllium is somewhat reactive, fairly reactive, but it also has a filled orbital. Now, what we're going to do is we're going to jump across that big gap of those transition metals in yellow on that periodic table. And the next orbital that we're going to fill in is boron. Boron is going to then have a single electron in one of the 3 p orbitals. This course is going to primarily focus on carbon, and carbon has another electron, but because of Hund's rule, where we have multiple orbitals, electrons are going to fill across those before coming back and filling up by themselves. Carbon now has 2 orbitals with a single electron in each, and that 3rd p orbital is empty. Now, there are going to be consequences that we're going to talk about in the future that pertain to this and why it matters. But if we keep moving forward, this will be nitrogen. Electron configuration, we'd say 1s2, 2s2, 2p3 will be nitrogen's electron configuration. Now, we've filled in each of these orbitals with their single electron, and now we can re-invoke Pauli's exclusion principle as we go from nitrogen to oxygen. And so we go to 2p4 for oxygen. For fluorine, 2p5. And if we want to generate the electron configuration for neon, again, we now have that filled 2p orbital system. It has electrons that are happy and satiated, and it doesn't want to behave in any ill way. And so it is now a noble gas. We have filled in all of these orbitals. If we move on to sodium now, sodium is a reactive metal. We've seen the videos where you throw sodium into water and it starts a little fire. And that is because sodium has that single electron in the 3s orbital. Now, it's reactive because sodium wants to get rid of that 1 electron so that it can behave more like neon. In the same way, lithium wants to get rid of that 1 electron so it can behave more like helium and be unreactive. Magnesium is a little bit more stable. You can buy magnesium metal in strips. It's somewhat reactive, but not very reactive. And if it does react, it becomes very reactive. There's a lot of potential energy in here for magnesium if it gives up both electrons. Jumping across that table again, we're going to ignore the 3d orbitals for the time being. And we are then going to fill in the 3p orbitals. We're going to stop at chlorine here. And so there's aluminum. Aluminum is a somewhat reactive metal. Then we go to silicon. Silicon and carbon behave in similar manners because, remember, we had 2 p electrons filled for carbon. Now we have 2 3p electrons for silicon. And so they have similar behaviors. If we go and add another electron, another atom, as we're adding up these atomic orbitals, now we have phosphorus. Then we can invoke Pauli exclusion principle. Now that we've filled up each of these orbitals, we can then go to sulfur. Sulfur and oxygen behave in a similar manner, and chlorine. if we were to draw out or write out chlorine's electron configuration, chlorine's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. And so chlorine's electron configuration is represented in this manner, where we have started with the lowest energy form, the lowest orbitals, and we progressively fill those in. If we look at the behavior of chlorine and fluorine, fluorine's electron configuration is a little bit shorter. But because both of these are missing one electron in that highest electron configuration, both of these systems behave in a similar manner. Both of these systems, both fluorine and chlorine, desperately want to get one more electron into that outer shell, that valence shell, so that they can become Nobel-like.